Hi, in this video we are going to introduce a new topic, hashing. Hashing is mainly used to implement dictionaries where you have key value pairs. It is also used to implement sets where you have only keys, set of keys. The great thing about hashing is it provides search, insert, delete, all three operations in big O of one time on average. So let's understand what do I mean by search, insert, delete. Say you have a set of keys, for example, phone numbers of the people. You want to quickly find details of a person with given phone numbers. So this is your search operation. You want to insert a new phone number as a key and value as details of that person. This is insertion operation. If that phone number already exists, then this insertion will override the previous value. Please remember, in hash tables or hashing, we always have unique values. All the values are unique. No duplicates allowed. So if a phone number already exists, if a key already exists, and if you try to insert again, it will override the previous key. Delete operation. Delete is simply deleting the key and its corresponding value from the hash table. Let us analyze other data structures, how much time they take for these insert, search and delete operations. All the other known data structures are beaten by hashing. Hashing works best when you have these three operations or a subset of these three operations. For example, if you want to do only search on a set of data, no other data structure will give you big O of one time for searching. Let's analyze other data structures one by one. Suppose you insert all the keys in an array. If you store the keys in unordered fashion, then your search is going to be linear time, big O of n. If you store the keys in sorted form, then your search is going to be big O of log n. But then your insert will become linear, because if you are using an array, then you will have to move all the items when you are inserting in the middle. Your delete will also become big O of n. So with arrays, you have big O of log n time for search, big O of n time for insert, and big O of n time for delete if your data is stored in a sorted way. If you store the data in unsorted way, then your insert and delete become big O of 1 on average, and search becomes big O of n. So with arrays, you always have one operation which is big O of n. At least one operation. If you're maintaining in sorted form, then insert and delete both are big O of n. Let's talk about other data structures. Although we have a binary search tree in the upcoming tracks, but let me give you some information about binary search trees also. Binary search trees, especially versions of the binary search tree like AVL tree and Radblack tree, they take big O of log n time for search, insert and delete. Big O of log n is still higher than big O of 1, especially when you have large data. This big O of 1 is going to take much less time compared to log n when n is really high. So hashing beats arrays, it beats AVL tree and Radblack trees because they are big O of log n, and it provides all these three operations in big O of one time. However, it does not provide certain operations which are provided by self-balancing binary search trees like Radblack trees or AVL tree. For example, you can find a key which is just smaller than the given key if the given key is not present. You can find a key which is just above than the given key in log n time if you're using AVL tree or Radblack tree. But with hashing, it is strict search whether the key is present or not present. Only that operation is big O of 1. If you have to find the closest value, that will take big O of n time with hashing. If you have to find all the values in a given range, that will also be a costly operation. You cannot get all the data in sorted order. If you want to print all the keys in sorted order, it's not an easy operation with hashing. So hashing you can consider as an expert data structure when you have search, insert and delete only. When you are not interested in closest values and you are not interested in sorted order. Here are three main areas where hashing is not used to store a collection of keys or key value pairs. One is finding closest value. If some key is not present, find the value which is just smaller or just greater than this. Keeping the data in sorted order, right? So if you want to keep the data in sorted order, if you want sorted traversal, hashing is not recommended way, because the order is not sorted according to the keys. So these two places we generally use AVL tree or red black tree, one of these self-balancing binary search trees, or maybe other versions of the self-balancing binary search trees. We'll talk about these in the upcoming tracks. The third area is prefix searching. So if you want to find out all the keys that match with a particular prefix, in that case also hashing is not useful, because hashing does exact key search. It does not do lower, smaller or prefix search. For prefix searching, there is a good competitor of hashing, which is trie data structure. Right. For strings, this trie data structure is an alternate dictionary implementation that also provides quick prefix search, which is not there with hashing. In this video, we introduced hashing. We talked about main three operations. We talked about the places where it should not be used. In the next video, we'll talk about applications of hashing.